Okay, 8.8, we're doing volumes with cross sections, but now we're going to do triangles and semicircles. In 8.7, we only did rectangles and squares. But to find the volume with the known cross section, we're still doing the volume of A to B of A of X, where A is the area of the cross section or the slice perpendicular. We're going to say the x-axis, but it could be either way. We just have to reframe it. Okay, before we do that, let's remind you of the area formulas. Okay, if you have a triangle, what's the area? It's 1/2 base times height. Okay, now if you have an equilateral triangle, it is 1/2 base times height, but we need to be careful about what the base and height are. Let's put it over here. It's equilateral, boom, boom, boom. Let's call each side S. So this is going to be 1/2, I'm gonna put this on the side. I'm gonna erase this in a second. 1/2 the base times the height. I need this distance right here. Okay, this is a special triangle. This is 60, 60, 60, which means this is 60. This is 30, this is 90. Okay, this side is S because it's the full side. This side, this little piece here is gonna be 1/2 S, which means the actual height of this guy is going to be √3/2 times S. So when I do the area, it's 1/2 the base, which is S, times √3/2 times S, which I'm going to rewrite up here as 1/2 √3/4 times S squared. And it's the 1/2 times the √3/2 that makes it do that. Okay, how about an isosceles right triangle? Isosceles right triangle, it's a right triangle. The legs could be S and S. If it's that case, then it's going to be 1/2 S times S, or 1/2 S squared. Okay, now if it's a circle, it's pi r squared. If it's a semicircle, it's going to be 1/2 of pi r squared because it's a half circle. Okay, let's go ahead and consider the situation in the example. Okay, our region is bounded by y equals x squared, which is this one down here, the lower function, y equals √x up here. And it forms the base of a solid. Find the volume of each solid with the given cross sections perpendicular to the x-axis. Okay, so we're going to do x-axis. So let's just start with that. V equals, okay, on the x-axis, I'm going from 0 to 1. Okay, now when I want to do the area using each of these sides, can I draw this? I don't think I can. I'm going to try to draw it, okay? So the cross section is this little slice right here. Okay, imagine you're looking down on this, and then if you kind of like stare up at it, it's like making these little triangles that are sticking up, and it's making more triangles sticking up and more triangles sticking up, and there's all these little triangles that are sticking up, and it kind of is creating a solid. Okay, but it's an equilateral triangle, so this is the length of one of the sides of the equilateral triangle. Okay, let me use the formula for equilateral triangle. It's √3/4 times the S squared. Well, each of the sides is this little cross section. The length of this cross section is this function, the square root of x, minus this function, which is the x squared. Okay, and then because this is a equilateral triangle, I'm going to square this side. Okay, and then I am doing this with respect to x, so let me give the dx here. Okay, this is the setup. Am I going to evaluate it? No, I'm not going to evaluate it. I'm just going to set it up. But you could put this in your calculator and get a definite answer. Maybe I will. Hold on. Okay, I did put it in my calculator. I got 0.0557 cubic units, but I more want to practice setting it up than evaluating it. Okay, the next one, same cross section, but we're gonna say it's an isosceles right triangle. Okay, so I'm still going from 0 to 1 because it's with respect to x. Okay, now it doesn't tell me which side is the base of the right triangle. So to make it easier, since it didn't tell me, let's just assume this is one of the sides, and then, can I draw this? I can't draw this 3D. But this little thing is like sticking up in 3-dimensional. Okay, so that's gonna be the side. Okay, so the isosceles triangle is 1/2 S. Each of the sides is still gonna be √x. minus x squared. Okay, and then squared, and then with respect to x, so dx. Okay, that's my setup. Okay, I can't always put it in the calculator. I will, hold on. Okay, I got 0.0624 cubic units, which seems fairly reasonable. I have no idea. Okay, now let's do a semicircle. Okay, I'm still doing with respect to x, so I'm going from 0 to 1. Okay, now a semicircle, I'm going to do 1/2 pi r squared. Okay, now with the r, I need to be careful. Okay, so if I look up here, this is my cross section. Imagine there's like a semicircle poking up like that. Okay, now from here to here is not actually my r, that's actually my diameter. So if I want the r, I'm not going to include the whole way across. I need to only include from here to here. Okay, so I know the whole way across is the root x minus x squared. But since I only want the radius, I'm going to divide it by 2. And this is 1/2 pi r squared, so I'm still going to square this, and then this is with respect to x. Okay, I can put this all in my calculator, but I think I'm just going to simplify the fraction a little bit to make it a little easier first. This is, I'm squaring the 2, so this is 4, and then times 1/2, it's actually 1/8 pi. And then I still have the root x minus x squared dx, and I am going to put it in my calculator just to try it. We're just setting up right now. Okay, so on the semicircles, just be really careful with the radius. Keep in mind the cross section is the diameter, and then the radius is going to be half that distance. Okay, so I got, when I put it in my calculator, I got 0.0505 cubic units, which is kind of similar to the volume of the other ones, but it does vary based on the shape. Okay, so just be really careful when you're setting these up, and that's it.